The next lesson is on reciprocal functions. So we're going to practice how to graph these. A reciprocal function, what that means is that our x, or our variable, is in the denominator. So a reciprocal means to flip it upside down. So instead of f of x equaling x, it equals 1 over x. So a lot of our horizontal stretches, compressions, and translations will appear in the denominator. The reason we're doing this one on its own is just because it has a lot of special features that we will definitely look at and examine. So first, I'm just going to make a very detailed table of values. So if I sub in -4 for x, I would have 1 over -4 as my first ordered pair here. And then -2, if I sub that in, I would have 1 over -2. 1 over -1 is just -1. This is what I'm worried about. So 1 over -1/2. What that means is 1 divided by -1/2. That's the same thing as 1 times -2 over 1 if I invert and multiply. So I actually get -2 for that answer. And -4, when I sub in 0, 1 over 0, I can't divide by 0, so I actually don't get an ordered pair at that point. 1/4, if I sub in 1 over 1/4, that's the same thing as 1 divided by 1/4, which is the same thing as 1 times 4 over 1. So I get 4 as my answer, and I get 2, 1. When I sub in 2, 1 over 2, and when I sub in 4, I get 1 over 4. So don't worry, we're not going to use that many ordered pairs every time. I'm just trying to give you an example of a reciprocal function and what the points would look like on this graph. For the first half of the points, what I wanted you to see, and I didn't use a third, I just used 1/4 and 1/2. I thought that would be easier to graph. What I want you to notice is that we went left 4 and down 1/4, and then we were down halfway when we went left 2. Every time I would go further and further to the left, my points are going to get closer and closer to the x-axis. So it might be 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/10. They're going to get closer and closer to the x-axis, but they're never actually going to ever touch it. The same thing's going to happen when I go down in this direction. I'm going to keep getting closer and closer and closer to the y-axis, but I'm never going to touch it. So the second block of points is going to show the same thing. So the same thing occurs over here. I have, I'm at 1/2, I'm at 1/4. As I go further, I'm going to be at 1/5 and 1/6 and 1/7, and it's going to get closer and closer to the x-axis. The same happens as I go vertically. I'm going to get closer and closer to the y-axis. It should look like a smooth curve, and it is kind of hard to do by hand when you're using pencil or whatever. I'm trying to show that my points come down and they approach the x-axis, but they never ever will touch it. I mean, that's going to be pretty hard on graph paper to show. An important feature here is that x cannot equal 0 because y cannot equal 0. We cannot sub in a 0 here because that is an undefined solution. So that is called an asymptote. Our x-axis and our y-axis in this case are both our asymptotes. You may have not heard that word before, but what it means is on a graph, an asymptote means that our values approach that axis. It's actually an axis. They approach that axis but never ever touch it. So the x-axis is an asymptote and the y-axis is an asymptote. So notice that this function only gives real values when x does not equal 0. Therefore, the domain is x such that x does not equal 0, and the range is y such that y does not equal 0. Y is still an element of all real numbers because all of the points in between are connected. It's also interesting to note that this function has no x-intercepts or y-intercepts. So when we are talking about our parent function, this function never touches the x-axis or the y-axis. That obviously could change if we were going to move this function side to side. You might see that the function does go across the y-axis, for example. Finally, one other thing that's kind of interesting is that this function is symmetrical about the diagonal lines on a graph. So this is actually the line y equals x, and this over here is the line y equals negative x. Those are the diagonals on a graph. So if you just sort of tip this sideways a little bit, you'll see that this shape is symmetrical along the line y equals x. It's also symmetrical along the line y equals negative x because it looks like it's reflected in the line y equals negative x. Another important characteristic is that as the denominator, as x gets really, really big, the fraction or the y gets really, really small. So as x gets larger and larger, the y gets smaller and smaller. Similarly, as x gets very, very small, the y gets very, very large. So when we look up here, as my x gets smaller and smaller and smaller, going in this direction, my y is actually going up and up, and it's getting much greater. So we have two asymptotes for this graph, which actually are the x and y axis. So the horizontal asymptote would be along the line y equals 0. So if I'm thinking of my graph, y equals 0 is along this, in that direction. So that is the horizontal asymptote. The vertical asymptote, if I think of this line, that's the line x equals 0. So that is our vertical asymptote. So we'll try and graph a couple of these. This first one is set up much like we would expect. One thing that I do sometimes like to see, I don't know, is the 3 maybe written out front. You could imagine that it looks this way. And then we have our function, which might be 1 over x plus 1, and adding 1 to the back. So this is still our vertical translation. This is still our horizontal translation that is with x. The reason I wrote this 3 out front is because that is our vertical stretch by a factor of 3. So here are some ordered pairs that we can use for our original parent function. I think the first thing, because it's multiplication, I would definitely want to look at the vertical stretch by a factor of 3. That means I have to multiply my y values by 3. So my x values are all going to stay the same. I have this point where I can't find a solution because I can't divide by 0. So I'm going to multiply all of my y values by 3. Remember when you multiply a fraction that 3 times the numerator, so I'd get negative 3 over 4. I'm just multiplying the numerator. I would get negative 3 over 2. Negative 1 times 3 is just negative 3. I'm not going to find that ordered pair. I'm going to do 1 times 3, which is 3. 1/2 times 3, so 3 just gets multiplied by the numerator, so that's 3 over 2, and 3 over 4. And then the same thing is going to occur. I'm going to subtract 1 from x, and I'm going to add 1 to y. So I usually just do these very slowly. I subtract 1 from each x, and then I'm going to add 1 to each y. So negative 3/4 plus 1, we end up at 1/4. Negative, that's like negative 1.5. And if we add 1, then we're only at negative 1/2. Negative 3, come up 1, we're at negative 2. 3 plus 1 is 4. This is like 1.5 plus 1 is 2.5. Maybe I'll just use a decimal. And 3/4 plus 1 is 1 3/4 or 1.75. Maybe that makes more sense. So I have my new points that I will plot. So when you see these points, it doesn't look like there's very many of them. You're going to get into this even more in grade 12 math. I know that my asymptotes have something to do with these ones, with how far sideways and how far up I went. So in this case, these are sort of telling me what my asymptotes are, -1 and +1. So I know this isn't very many points, but you can kind of imagine what the curve is going to look like. And this curve over here, what it's going to look like. So I might just kind of sketch in where my asymptotes look like they will be. I think it is the exact same shape. There wasn't any reflections or anything like that. I just sort of moved the same shape. I didn't really have a lot of points. I could have added maybe -5 and -3. I could have added more points to help myself, but you'll get used to this and you imagine what the curve looks like, and it's going to approach. I have this horizontal asymptote at y = 1, and I have a vertical asymptote at x = -1. So if I was going to look at my domain and range, let's just talk about that. My values y can never equal 1, and x can never equal -1. Otherwise, all of the other points on the graph are fine. So the domain is the set of x such that x can never equal -1, and x is an element of all real numbers. Because these are our asymptotes, they show up in our domain and range. Y can never equal 1. Y is an element of all real numbers. So vertically, I am never going to have any points actually equal 1. I'm going to have some above and I'm going to have some below. As well, this time I do have some intercepts. So for example, I notice right here that my graph does cross the y-axis. And it also as well crosses, I don't know if I graphed it very well. I think it's around here. I'm going to cross the x-axis. So another way that you can also always remember to find x and y intercepts, if that helps, just as a little aside, you can let x = 0 and let y = 0. If you wanted to find any intercepts out, if x = 0, I would have, if this was 0, 3/1 is 3 plus 1, so y = 4. That would be my y-intercept. And if y = 0, this would look like this is my y, so this would be 0. What would happen there? 0 on the left equals 3/x plus 1 plus 1. If I'm going to let y = 0, I'm going to move my 1 to the other side. This is just extra information you could find. I'm going to cross multiply, so that would give me -1 times x plus 1 equals 3, -x minus 1 equals 3. So -x, I'm going to move the -1 to the other side, that's 4. Divide by -1, so x equals -4. Which is what I think I was supposed to show up here, that my x-intercept is at -4. That is for any graph. You can always check to see what the x and y-intercepts are, if there are any. By letting x = 0, you find the y-intercept, and in your equation you let y = 0, you can find the x-intercept. Sometimes you don't like the way that your function is written, so what if I first did... what if I put the 1 at the back? Because I know that that's my vertical translation and I'd like to see that at the back. As well, maybe in the denominator, I'm so picky, I'd like to have that x in the front. And then I also think, okay, wait, I can't have anything ever beside my x. This does not mean +1. I need to always factor out anything that is in front of my x. So that would look like x minus 1. So just from an equation standpoint, I see there's two negatives here and they're outside. So it would give me the exact same graph if I just wrote that as x minus 1 in the denominator plus 1. So two negatives, just thinking of it as if you were looking at this as an equation, this graph would give you the same thing as this graph. So if this becomes our new function, it's a little bit easier to deal with right now. I'm going to use the same points. So sorry, I'm running out of room there. There's the same ordered pairs I'm going to use again for this type of function. If I don't have any stretch or compression numbers, all I really need to know is that I go right one and up one. So even if you wanted to just imagine our original function or our original set of points, we just have to move the points right one and up one. So I have to add 1 to my x's and 1 to my y's. So I think you maybe could have tried to do this one without a chart. I've added 1 to all of my x's, and then I have to add 1 to all of my y's. Sometimes it's a little harder with fractions. If I'm at -1/4 and I add 1, now I'm at 3/4, but maybe you'd rather have decimals. If I'm at -1/2 and I add 1, now I'm at 1/2 or 0.5. If I'm at -1 and I add 1, I'm at 0. 2, and if I'm at 1/2, now I'm at 1.5. And if I'm at 1/4, now I'm at 1.25. So I think that doesn't give you a lot to go by, but you can kind of see the shape. Again, I know that 1 becomes my asymptote and +1 also becomes my horizontal asymptote. So if my asymptotes are at x = 1 and y = 1, my domain is going to be the set of x such that x just can't equal 1. And the range is going to be the same idea that y cannot equal 1.